Welcome, everybody. I'm Mike Mahedy, Solutions Advisor for Verdigris Technologies. And today we're diving into a problem that's costing data center operators millions of dollars and leaving expensive GPU hardware sitting idle. And most people don't even know what's happening. With me is Jonathan Chu, my co-author on a white paper that's proving very timely with respect to AI workloads and data centers. John, thanks for joining me. Give us a bit of background about yourself.
Yeah, very nice to chat with you, Mike. I am co-founder and CTO of Verdigris. We're a provider of energy monitoring, energy services within data centers. I've spent a lot of my career back in semiconductors, then moved to some awareness in power distribution, really excited and interested to get intelligence onto the electrical side so that we can all make better decisions with how we use that resource.
Awesome. Well, let's start with the basics. You've spent a good bit of time studying how AI workloads behave differently than traditional data center loads. What's the fundamental problem that you're seeing?
Yeah, we're seeing a big, massive shift. Obviously, AI is an exciting field, has a lot of potential to change the way we live and work. But at the same time, we're seeing that AI data centers are both a huge amount of density, orders of magnitude higher density and growing than traditional data centers. So that's one challenge, just getting enough power. But we're also seeing a massive transient within data centers. We're seeing loads move 65% of peak power in just under 10 milliseconds. That's faster than any existing telemetry really sees at scale. Traditional data centers were really built for these steady, predictable loads, and AI training is the opposite. It's like goes from idle to full throttle, many times a second even, and it's very hard to track, predict. It has untold and unseen effects on some of these traditional power distribution networks. So that's a challenge for the industry.
So what we're seeing basically is a new problem.
Yeah, absolutely. When you look across traditional pieces of equipment, generally, as equipment gets bigger, it's more mechanical, it's a bigger flywheel, it moves more slowly, it has more control logic around it to kind of keep it flowing predictably. So as these loads tend to aggregate together, they statistically balance out and become very steady. Seeing something very different in AI servers, huge coordinated transient events across all these processors, and it's really kind of flipped that traditional steadiness on its head.
Interesting. So you mentioned, under 10 milliseconds in the paper. It says 8 milliseconds. Help our audience understand that in the context of power infrastructure.
Yeah. So in North America, the standard alternating current cycle is distributed at 60 hertz. That roughly means one power cycle every 16 milliseconds. So if we're saying 8 milliseconds, it's really in one half a power cycle, which is very fast. By the time you actually see that in telemetry occur, your breaker may have already tripped.
Wow. We're not going to spend a lot of time today talking about the fault detection aspect. We actually have a second webinar you and I are going to do on fault detection, so we'll save more of that for that webinar. Let's talk about cost. What does this problem cost data center operators? What are we seeing?
Yeah, the typical megawatt of compute costs anywhere from 5 million to 15 million in capital to create. So you're saying a 100 megawatt facility taking $500 million to build at least. Because operators can't really see or manage these transients, they really have to derate that infrastructure by quite a bit, 30, 40%, just to kind of keep the lights on, keep it running. Because they don't want to get into a position where these peaks are causing problems with their power delivery. So that right there is 150 million in hardware that's sitting there that it just can't be used. Like that capital has been spent to create that capacity, yet you really can't fully consume it because of these peak transients.
Wow. You also mentioned, in the paper about stranded capacity. How is that different than just sort of conservative planning?
Yeah, and conservative planning is really about risk management, which is a huge issue with infrastructure. There is typically some amount you leave on the table. There's the National Electric Code, which says this is how much you should be consuming. Then you want to build in some natural margin because that's a planned risk mitigation, right? You're willing to say, I know I'm running at this level. I want to put in an extra 10% margin just in case, so I don't run into trouble. And that's worth it for me because the amount of downtime I avoid is worth more than the capacity left there. That's all standard business for data centers. The change with AI from the standard practices with these AI data centers, we don't know how close we are to that margin, right? We know sort of it's highly fluctuating. We know what kind of the max peaks are, but we're seeing it at like a minute level or a secondly level, but not these really fast transients. So there's this unseen sort of boogeyman of sorts. That's these transients might pop up and flip like a medium voltage breaker pretty quickly, and you can't be caught off guard there. So you kind of have to leave a little bit extra there, and that's just an incredibly expensive proposition to leave that extra on the table.
Yeah, that is expensive. I mean, why don't we just build more power infrastructure? Why isn't that the answer?
Yeah, a few reasons. Power infrastructure takes a long time to build. Um, you know, 18 to 36 months to deploy, cost 50 to 75 million to do like 10 megawatts. And for reference, over the last 100 years, right, our history of power build out, we've built a total capacity on the US grid of about 850 gigawatts, right? AI demand workloads over the next 2 years are already forecasting another 100 gigawatts of build out, right? So now 100 years for 850, and then in 2 years, you want to build an extra 100. You can kind of see where the rate of build out doesn't quite match our historical record. But more importantly, it doesn't solve the root problem. Even with more capacity, you still can't manage these transients. You're still derating to stay away from them. You're still spending all that capital to create that capacity. So you're just sort of pushing the problem around and not solving it.
Fascinating, just fascinating. The paper we referenced, the Llama 3 model. Can you tell us a bit more what happened there?
Yeah, in the Llama 3 training model, they outlined what it took to build this foundational model. It took something like 54 days and tens of thousands of GPUs, but they really dug in. They looked at some of the causes of what was making training fail and what issues they hit, how they worked around it, and kind of did a detailed study that really hadn't been done before on the AI side. So a few things there, they noted these rapid transients. They noted when these models went to write and synchronize state, they would all stop, they would all write that state to disk, and then they would all start up instantaneously. And Meta noted that that was a huge surge in current. That was a very difficult thing to manage. The other thing to recognize is the percentage of failures on GPUs versus traditional CPUs is much higher, right? And kind of points to some of the stress that hardware is putting on the power delivery and some of the added instability that that's causing. And since the new field, a lot less knowledge about where those failures are coming from.
Interesting. So we had the famous stadium stomp effect
Mm.
with the Meta Llama 3. We also talked in the paper about, token production being a pain point, and we've certainly heard that from folks that we've talked to in the industry. For people that might be watching this that aren't deep in the AI world, what does that mean, and why should data center operators care about it?
Yeah, so tokens are kind of a fundamental unit of work for AI training loads. It's how you measure how much compute is required. In a lot of ways, all models use it as a way to measure how much that training costs when you use these AI tools. The more tokens per second means faster training, faster inference, just better business outcomes. NVIDIA recently showed with their Dynamo um, utility that you can get 2 to 30x more inference training from the same hardware. And they did that using millisecond scale orchestration. They're saying if you can move these jobs around really quickly and manage that, you can get much better outcomes in terms of token throughput. And our belief is that translates to power scale as we start to orchestrate with awareness of how much power these jobs are consuming. We can make better use of the total capacity we have for longer durations of time and improve the token throughput.
Interesting. So token production is constrained by power. Anything you want to add to that on how that's possible? Um, you know, any additional commentary you want to add there?
Yeah, we've always seen that data feedback really makes us able to do processes more efficiently. So we saw this with a utility from Meta called Dynamo that used power feedback, and this was just on 1 or 2 seconds, but that saved about 8% of or improved capacity by about 8% just by getting that feedback in. Back to the age of vehicle manufacturing, you had Ford and Toyota collaborating using the Kaizen process of continuous feedback, right? As you look at those metrics, you start to see where to improve. So yes, when we look with the right instrumentation at power, especially for these AI data centers, we see that there are gaps in that full capacity usage. And by feeding that back into orchestration, we see a lot of potential to unconstrain these jobs from their current power envelopes.
You can't improve what you can't see, right?
Yes.
Which sort of leads me to the next question, about sampling rates. We talked a lot about it in the paper. Why does this matter so much, in particular for, the types of things that we're seeing with these transient, power spikes?
Yeah, particularly with how fast these power spikes move, you think about a pretty traditional meter will do a sample per minute. Sometimes on these legacy BMS systems, it's a sample every 15 minutes. So you're trying to look at like a hummingbird's wings with a still camera, right? Something that will just capture one image. You're really not seeing what's happening with those wings flapping. So with these traditional meters sampling even on a second interval, these transients happening in the 8 millisecond spectrum, those samples are really getting averaged in, and you're really not seeing what the true transient effect is. So that's 125x mismatch. You're essentially flying blind.
So just to be clear, these traditional systems like Schneider and Eaton, these big names, they're great for traditional data center workloads, right? This isn't about them being bad products.
Yeah, exactly. They are great products. They're just designed for a different world. like one where your biggest power spike was turning on a row of servers or a giant chiller plant. Takes a few seconds, 2 minutes to ramp up. So you kind of see that one transition, but it's predictable. They do what they were designed to do well. Facilities teams leverage them to understand critical failures that are happening within a site. What they aren't doing now is providing the continuous telemetry at the resolution required to see some of these new problems. So these AI training models broke all the assumptions of what these designs were based on. And it's like trying to use like a calendar to time a sprint, right? You really need that stopwatch to do it. It's the wrong tool for the job.
That's a great analogy. I love that. So what does the right tool look like? What are the key things you think that actually matter specification wise?
Yeah, we're seeing needing that high frequency sampling somewhere between 2 to 8 kilohertz. We're seeing needs to get that telemetry in a way that's scalable too. So plenty of tools are showing waveform capture that is getting one point in time. But because these transients are continuous, because these AI loads keep evolving, you have firmware that goes out that completely changes the behavior of these models. You have new use cases for AI. There's a lot of study on big switches back and forth from text to video, and some memes going around drastically changing profiles. So you really can't take one point in time and say, yeah, my design is good. You need that telemetry constantly, and you need to be able to cover all of operational time. So really, it's getting to the metrics within those frequency ranges that matter, and then being able to scale those metrics across lots of instances, across large periods of time, in a way that can attract the right attention and create the right feedback, whether it be some machine feedback or human feedback.
Yeah, I was just going to mention, we're talking about massive scale in some of these, AI data centers, just things that we couldn't comprehend before, right? Um, let's circle back to Meta's Dynamo system, and I think some of that research was done in 2016. It seems like that's early feedback that these faster feedback loops work. What can you shed any more light on what they discovered?
Yeah, so Meta found that they were um, getting they were hitting a capacity limitation as well, and they saw the need that getting feedback telemetry on a faster basis helped them unlock that capacity. So they created their own system that would take sort of secondly updates from their telemetry, bring it into an orchestration layer to do fast feedback. They might change orchestration so that they limit their power and avoid breaker trips. This allowed them to increase the amount of jobs they could deploy into their cluster without any SLA violations, without stability issues, without really creeping into that margin more than they need to. They still had confidence that they could stay away from that breaker trip because the orchestration understood where that limit was. So yeah, the insight is that was pre-AI, so they didn't have as many problems. They were already pretty optimal in capacity, and that visibility was still 100 to 1,000 times slower than transients and the kind of telemetry we're talking about now. And they still got an 8% improvement on that. So you have to wonder what's possible when you really ramp it up on today's problem. If you apply the same techniques, how much is there to unlock?
Yeah, really interesting, and so that more granular, timely power information obviously increases capacity utilization. The paper, we propose something called hierarchical token based orchestration. And one thing I want to sort of be clear on is, I think folks may be wondering, why can't we just orchestrate based off the power information we get off the GPU? When we talk about, GPU versus, rack, row, explain why this hierarchical, um, you know, token orchestration is important. What does that mean in practice from, like, all the way up to the facility perspective?
Yeah, and it's a tricky concept, but you have a lot of activity in a data center that's happening at different time scales. So at the GPU level, you are seeing microsecond level decisions flying around that board in terms of uh, jobs and what is happening in the control circuitry there. At the rack level, that coordination is in the milliseconds. On the cluster level, you're probably managing across dozens of racks in tens of milliseconds. At the site level, you're in the hundreds of milliseconds to maybe even seconds to move some of these loads around. And at each level, you're also talking about an order of magnitude more power. When you look at the hierarchy too, there are different sets of constraints. At the whole facility, you have this medium voltage coming in. That might be one or two big bottlenecks with really fast, very critical breakers on them. As that comes down into the data center, you have rectifiers, you have UPSs, batteries, you have redundancy. All of that has different meaning for capacity and what's needed. So it's not just always managing the overall data center. You're managing how much uh, budgeting is done, even within these rows and even within specific racks. Um, so what we are proposing is a hierarchical-based system. It's really difficult in a centralized way to manage all of this because you're making so many decisions at so many different levels, at so many different time horizons, that some of them become impractical. You certainly wouldn't want to make a board level decision from some centralized site level control software. So we're posing tokens as a use of representation of power, how much power over how much time being used. There's some predictability there. Some jobs are already sort of pre-assigned some set of tokens, and as they consume them normally, they get credited for more usage as time goes on. If they go to exceed that amount, they have to go back and get more from their localized orchestration layer. So you can start to get kind of rack level, cluster level orchestration because these tokens are sort of passed down as budgeting, and there's some sense that these localizations will start to derate when they start to run out of that token capacity. So you can really plan out that budgeting earlier in prediction, and then you can enforce it by seeing that you don't have enough budget in this localized area to run jobs. The key is really that, yeah, local decisions happen fast and they're coordinated by a bigger picture that's managing all of these.
Yeah, I was just going to ask you, how do you coordinate with existing protection equipment? Aren't you worried that the orchestration, may clash with the breakers? How do we prevent that with this hierarchical system?
Yeah, this orchestration system with the tokens is aware of the protection equipment, so it would understand like that budget is related to what those breaker limits are, and it's ingrained in the orchestration. A lot of the token throughput and assignment is given by the orchestration, so that when there is a signal to say this subsystem needs more energy over time than expected, that's where the orchestration comes in, and it can adjust that schedule to say, hey, I either can give you more tokens because nothing's really happening, or maybe I can move some loads around. I can derate some places, other places, to provide that budget.
You talk about protection coordination quite a bit in the paper. You just mentioned it. Um, for operators, that are living with NEC code and breaker curves, what do they need to know?
Yeah, the orchestration really is needing to be more protection aware. It needs to understand those breaker trip curves, their magnetic limits, where they have some flexibility and where they don't. So in the architecture we're proposing, those orchestration responses finish in about 70 milliseconds, which is kind of within that range of where you want to be catching some of those events before they cause critical breaker trips. So the key principle is just the orchestration needs to be faster than the protection. And if the orchestration fails, the protection will still work normally.
Okay, that's a great principle, to a key takeaway. Um, I think we talked a bit about how we budget tokens, but is it possible to go over budget?
Yeah, so that's a key concept in it. Where it has to be a deliberate decision, right? Where in the past, if one training job for some reason is now taking significantly more energy over time than it had before, we don't just want to let it run and say, well, let's just see what happens. That's where it has to then go back and say, hey, I'm running hot. And that would necessitate orchestration to say, well, either I have to come up with the budget for you to continue running, or I'm going to quickly uh, meter and derate how much work you're doing so that you can stay within budget. And that's a decision that you want to be making deliberately.
That's great. So practically, what does this look like in a data center? What kind of hardware and software are we talking about?
Yeah, you need several things. First, you need meters that sample at a high frequency per second, and that includes latency, right? It's not like you're showing what you sampled seconds ago. You're showing something that happened very recently in the last few milliseconds, and you're making that visible. Second is edge processing. There's this idea like if I have a rich hierarchy of these devices, I'm going to find myself passing around thousands, if not hundreds of thousands of messages that are all really critical that need these millisecond timelines. I'm going to saturate my messaging fabric. I might not be able to guarantee the quality of service I need. So you really want that edge processing to make those local decisions, make the calculation for those tokens and budgets locally. And then only when you exceed, that's when you send the messages out. So you're bringing down the number of messages you need to the exceptional cases where you're not meeting the budget. And that brings down the traffic by a few orders of magnitude. And third, you really want to open up these APIs and integrations. One of the key challenges with AI data centers is a lot of these orchestration engines and a lot of these facilities telemetry pieces to live in completely different worlds, right? So open up the communications, open up the APIs, make sure you can integrate with your GPU schedulers, because this power-aware orchestration is going to certainly be one of the key things that will allow our data centers to continue to operate.
Great points all. You talked about the edge processing capability, and we talked about it in the paper. Why can't we just send this high frequency data to the cloud and process it there?
Yeah, there's several reasons there too that just come down to sort of raw physics and timing, right? If you're trying to make a decision in milliseconds, you really can't afford to take those tens of milliseconds to get to the cloud and back, right? Even with the best, content delivery networks, that's a tall ask to ask for that predictability. At 8,000 samples a second across hundreds of thousands of meters, you'd also just saturate your network bandwidth sending raw data, right? You need to transfer all that data. You need some massive amount of processing to even go and look through all that data in real time, right? It's just so much cleaner to have that intelligence at the edge, and that meter just needs to be smart enough to understand the data and then detect the events, run customer logic and just make those local decisions.
But in the paper, we talked a bit about customer programmable logic, and what does that enable the fixed function meters can't do?
Yeah, there is a lot that's moving forward very quickly within AI or neocloud data centers. And that means there's a lot of variety in what actually gets created. So we're not seeing very consistent architectures with very consistent orchestration layers. There's a lot of different decisions being made. There are great community forums like the Open Compute project that help to coordinate these and help to share those. But because the industry is moving so fast, there are quite a few data centers moving ahead of where OCP is currently at. And it's really infeasible at this point in the market to just put something out and say, here's a standard that pushes this leading edge, but also has everyone conforming to the same interface. So in recognition of that a lot of these data centers are creating their own logic and own modification to orchestration, having that customer programmable logic on the device in a way that's transparent, have high frequency interfaces to the local data, but the ability to get that connection to the endpoints and to the logic that our customers define. That's a key way to enable this, especially for the leading edge that we're on right now.
Yeah, and as we've heard from customers across our conversations, that speed to market is the key component, right? In terms of being able to deliver capacity immediately. So some of these organizational bodies like OCP you mentioned may be a little bit behind in terms of what they can propose as a community. So yeah, interesting takeaway on that. Let's talk about results here for a minute. What kind of improvements can operators actually see when they implement this approach?
Yeah, some operators that we've talked to, without naming names, are seeing somewhere between 8 and 20% when they deploy these kinds of systems. Some of them are seeing as necessary. They were already pushing the boundaries and they needed these. Some of these, they allowed them to push the boundaries and gain some of that capacity. So there's some variation there in those numbers. Yeah, in one case, an operator avoided $30 million in power infrastructure build out by unlocking the existing capacity that they already had. Critically, this was with no SLA impact, no stability issues, no breaker trips or risks for production workloads.
And obviously now we're talking about Verdigris hardware and software specifically. How quickly can operators see these results? Like, what's the implementation timeline to sort of data value, right? Obviously, there are change management concerns in the data center. All that notwithstanding, like what's the time to value for the installations?
Yeah, I'll give maybe a few answers here based on what we're seeing. To get meters installed, it's a relatively quick process. For Verdigris meters, you could do it within a month, and then it's just about integration into orchestration, which can be pretty fast. So on paper, it's a pretty quick timeline. We're typically seeing what we would call greenfield data centers, new build outs, right? And those are coming with pre-configured hardware where they're expecting all the metering and all telemetry being built in. So that build out schedule, obviously with the race for AI and some of the equipment delivery schedules, is by build out time. So I think in existing data centers where operators are looking to retrofit some of this operation, it can be pretty quick. And then for the new ones, it's just about the pace that the data center is built out.
Great. Thanks for the clarification on that. Let's switch gears here a little bit. In the paper, we proposed this micro PMU for compute standard. What's the vision there?
Yeah, so phaser measurement units, or PMUs, really revolutionize the electrical grid in a few ways by providing synchronized high-frequency metrics and measurements across the power grid. And we really are seeing the same need for data centers. So this micro PMU for compute standard would define sampling rates, accuracy requirements, communication protocols, API specifications, just everything you might need so that any vendor can help build towards this equipment that just works together. Right now, it's a bit of the Wild West. Standards are accelerating adoption and innovation, but to get to a point where a lot of these higher frequency metrics are exposed in the right way really requires a lot of coordination.
Let's talk about that a bit. What's really required for a broader industry adoption, and who needs to be involved, do you think?
Yeah, this comes back to like one of the comments I made earlier, is how well connected a lot of these are. So, the industry is aligning behind Redfish as a protocol. It does have some legacy protocols that it uses too. But what we see is when you go to vendors, they universally implement some of these protocols, Modbus, Redfish, but when you ask them how their customers are using that, the answer is invariably, I don't know. Right? And everyone's looking for it. Everyone wants it to be there as an option. But when it comes to who's pulling in that data and what they're doing with it, it's a completely different person in a different room that's not talking at all to the vendor. And that's kind of been one of the gaps. And what I was saying before is often the persona that is putting in the telemetry in a traditional data center doesn't work with, may not even know who is doing the orchestration, right? It's several silos away. And that's the part that really needs to be broken down. This information on telemetry is absolutely critical for this power-aware orchestration to take place. And I think we are starting to see that now. Some of the AI data centers that are really pushing forward, you see these tight collaborations with orchestration that I don't think you've ever seen before. And some of the streamlined, get this hardware in, measure this specific point at this specific speed so I can do something with it. Like that's happening more and more. But industry-wide, we're looking for that wall to be broken down.
Yeah, I was just going to note, I think we're seeing a shift too, and you and I have noticed this in conversations with folks, where there's definitely a shift toward more software development in the data center. So a software development first approach to solving data center issues sort of from the ground up, right? So maybe not necessarily using traditional BMS or EPMS, or even some of the traditional standard Modbus BACnet type of protocols that are there. So your comment about, hey, yeah, I'm a PowerShelf provider, and yes, I provide the information out via Redfish, but how is the customer using that? I think is there is a disconnect. The industry does need to come together. So sort of building on that, where does this go next? What do you think is the 2 to, let's say, 3-year vision even on this?
Yeah, there's 2 big directions. First, having predictive power management models. I think we are seeing that the hardware is changing rapidly, the AI models are changing rapidly, the customer use cases are changing rapidly. So these models of what happens when you send these kinds of orchestration commands to a cluster need to be built so that we can understand and plan for the power consumption, using these models to forecast the density of power spikes, the overall IRMS, the ramp up, the cool down, how to stage a lot of these processes in parallel so that they operate within the physical constraints of the data center. That's It's a critical piece that is just starting to evolve now. And second is the integration into those frameworks. Um, you know, PyTorch or TensorFlow having native power awareness built in, or some of the orchestration software, GPU stack or Slurm, having an understanding of this is how I budget power being distributed to a cluster, and modeling how to fill up that capacity evenly. And to that feedback loop, some of the really low latency feedback to allow orchestration to back off when it's approaching critical limits. So I think both upfront modeling to do a better job in filling out that capacity, and this high frequency, really almost semi-instantaneous feedback to come back from the boundary if you happen to encounter more power than you're expecting.
Yeah, and great points. And this also, obviously would tie into broader sustainability goals. You and I are aware, of course, I'm sure most of the audience is aware of, pushback on AI's, energy footprint, carbon footprint, et cetera. Anything you want to mention on sort of the benefits here towards sustainability?
Yeah, obviously the increase in density, I think roughly the data center market is like 4 or 5% of the US grid, expected to grow to 12% or so. So it's a big problem to be sustainable and want to consume that much more power. So, on the surface level, it looks like it's in conflict. But there are some bright spots. AI workloads are able to be moved, are not so critical in terms of real-time nature. So you are seeing a lot of companies doing grid interactivity with data centers, ways for that grid operators can utilize some of that flexibility of compute to stabilize the grid. And that has potential for being a strong positive. So if we can really balance, the efficiency and power generation associated with this AI data center, there might be strong positives in the ability to manage overall grid energy using some of this real-time responsiveness.
So there's the top down, and we're looking at sort of a bottoms up to tie it together. That's great. John, if you could leave the audience with one key takeaway, what would it be?
Really, you just can't optimize what you can't measure. And this AI infrastructure race is not just about who can deploy the most GPUs the fastest. I think the companies that are doing that now are quickly seeing that there's a way to run those efficiently and safely at full capacity that they're really having to put attention to, and it's a balance of how much speed you get versus how much value you get out of them. So I think the operators who are implementing this real-time power visibility are going to have something like a 15 to 25% capacity advantage over competitors that still use traditional monitoring. And I don't think it's a small edge. It's going to be potentially huge sums of money. So that percentage is significant. And I think that's going to be a trend going forward, to see more of that real-time power visibility towards capacity management.
Thanks, John. Really appreciate you walking us through this. For everybody watching this, if you're running a data center and dealing with AI workloads, or planning to, this is something you need to understand. We're making the full white paper available for download at verdigris.co. And John and I are both on LinkedIn if you want to continue the conversation or have questions specific to your environment. The bottom line is this: AI training is breaking traditional data center power management, and the gap between what's possible and what operators are achieving is massive. The question isn't whether you need real-time power visibility, it's whether you'll be an early adopter or watch your competitors unlock capacity while you're stuck derating. Thanks for watching, and we hope to see you in part 2 of our webinar.